Welcome everybody to this presentation by John Falconer at the University of Colorado. Just give a little bit of an introduction to him. He is a professor, now emeritus. He's focused for his research was on zeolites, but he's also had a really big impact in online education and distance learning. Some of his efforts are through LearnChemE, and he also curates the cache.org teaching resources. Through LearnChemE, he's developed a library of 1,600 screencasts, 2,000 concept tests, 185 interactive simulations, and more than 35 interactive self-study modules for chemical and biological engineering courses. And these screencasts have been watched many millions, tens of millions of times in the last few years. So definitely had a big impact, and he's working on developing active learning for topics like thermodynamics, kinetics, material, and energy balances. So with that, I'm going to go ahead and turn it over to John for the presentation. He welcomes any comments or questions throughout, so feel free to leave the chat window open, and we'll try to work through some of those as we go. All right, John, let me go ahead and have you start sharing.
Okay, can everybody see my screen?
Yeah, looks
good. Okay, so what I was going to do is talk about 20 minutes of something I put together last night so that give you some idea of what's available as more places are going to canceling classes, as University of Colorado has done, so everything is now online for the rest of the semester. And instead of everyone having to reinvent the wheel as it is, there are really quite a few resources that can be used, and I just want to briefly talk about them and then try and answer questions about, you know, how to use them or what's the advantage, etc. So let me first just give you the links that are the ones that are useful. The LearnChemE site is mainly what I'll be talking about. Now, the screencasts that John mentioned are available on YouTube, and particularly students often just go there to search rather than going to LearnChemE, since it's, you know, very good for searching. And then the CACHE organization has a teaching resources center for a number of courses where it links to other sites. So it doesn't have original material, but it links to useful sites. Here's how someone else teaches a course, links to some of the LearnChemE materials, etc. And it's particularly useful to someone teaching a new course, but certainly there are, for example, screencasts other than just ours that are linked on the various courses. And so the idea is that, you know, how can you potentially use things like screencast? And instead of just lecturing online, because I think lecturing in class doesn't work very well, so lecturing online is not necessarily going to be any better, assigning students to watch screencast, which is what I do before class, and typically about 3 screencasts is more than sufficient to constitute what would probably be a 50-minute lecture in terms of the material covered. So it's much more efficient time-wise, because of course during the screencast students are not interrupting and there's not all the other things involved. And screencasts, you can see, are very short, typically 5-6 minutes each. So I'm going to talk a little bit about screencasts and how they you know, the best use is have students watch them offline. I mean, not offline, watch them, you know, from the website, but not as a group in what, you know, would be an online class. The other thing I think particularly useful are self-study modules. They're made to be interactive. They include screencasts and lots of other things that I'll tell you about. And that there's something for students to do on their own. Take about an hour to complete. We don't cover as many courses as the screencasts do, but I think they're useful. And then interactive simulations. And for those you might not be familiar, a number of them are sort of like lab experiments, and you can certainly be treated that way, particularly if labs are canceled. It's not a perfect substitution, but it might allow, if appropriate ones are there, coverage of material that otherwise you couldn't do. And if I were to do just an online class during that online time when all the students are there, I would devote it to things like concept tests and these interactive simulations, and I'll talk about what each of those are. So, as John mentioned, we have a lot. We have more than 1,650 screencasts for a lot of topics. For those you might not be familiar, let me just show you one so that and I have the volume. I will make sure so the volume's turned off. But the screencast, you can see this is only 5.5 minutes long. It's someone talking. You can't hear the sound, so it won't confuse you with me talking. Someone talking, it's handwritten, and it's the kind of thing you might do in class. And again, it's something that students can watch on their own so they can control the speed. And that's one of the huge reasons for doing this, is that now students have their own rate of watching them and pausing and rewinding.
John,
So,
I had a question for you here.
Yeah.
So you've helped a lot of others do screencasts, not only done your own. What are some tips that you have to recommend for somebody who's just starting off with online screencasts? You mentioned 5 to 10 minutes, but what are some of the other things that you would recommend to make effective screencasts?
Yeah. So make all the screencasts with a tablet PC. Don't try and make them what you might call professional. In other words, I've had someone that made a few screencasts for us, but this person literally spent 40 hours because we get 3/4 way through, make a mistake or say something wrong, start all the way over. You want to try and just do one take. And if you have mistakes and you notice them, then you just mention, oh, that number should have been 7. That's fine. It's easy to edit, but you don't have to. I typically have somebody edit them for me and take out all the dead times, and I'll be 3/4 of the way through and say, oh, I didn't mean that, and they can take it out. Use first person, and say, hey, I'm going to do this. Hey, we're going to look at this. I use OneNote to make the screencast because it's easy to write on the screen, and that's what I'm using here for this webinar. And then I have a sort of handout I can send anyone if they just email me that has more details and suggestions. Don't put in extraneous, nice to know information. Even though it's like, well, that should get students more interested. The studies say people learn less when that extraneous information's in there. So keeping them short is important, and that's one way to do so. Explaining all the symbols. There's a whole list of things. Maybe it's easy. I can either send that to John, or I can post it on. It might be already on LearnChemE. There's a lot of suggestions on LearnChemE that I'll show you a little later of how to make screencasts, what software to use, that kind of thing.
Thanks, John. That's helpful.
Okay, so just go to the LearnChemE website so you get an idea that we actually have screencasts for a number of courses. It's not evenly distributed, and we're still adding screencasts and hopefully getting other people to make screencasts in some cases for us, but we cover most of the core courses, and the ones with have a very large number of screencasts are courses that I teach. so I can't make them for some of these other courses. But it gives you an idea of what's available. And then if you go to the website, then they're organized by textbooks, two of the commonly used textbooks, and then they're organized by topics, where each of these is a link to the screencast. So I think in some ways this is perhaps the most valuable thing if you're going to online courses, that students can watch these instead of you having to start from scratch, make your own screencast, but certainly it's not unreasonable to make your own short screencast. And one reason why I thought it's worth mentioning, because if you haven't used them, anytime you make a change, students can be resistant or very resistant. However, with screencast, since I started, overwhelmingly students, these are just comments I took off in the semester feedback. And what's I think significant is these were for thermodynamics. And as I jokingly say, no student uses the word love and thermodynamics together. And so I think one of the values is that students are going to watch them, and they like using them. Students come in and tell me, hey, I was watching this, I have a question, that's something I saw. So if the whole message was just this, I think using screencast is a really effective way when you're going now to more online. So here's the link on LearnChemE to tell more about preparing screencast. Talks of, so various tips. We use Camtasia, so it has tutorials on using Camtasia. And because I use OneNote, then it has some tutorials using OneNote. And then certainly I'm happy offline later to answer questions, give you more feedback on using them. So the other thing that we spend a lot of time on are these interactive simulations. These are computer simulations. The idea is similar. Some of you may be familiar with the physics community has made a large number on the PhET site, P-H-E-T, which happens to be also at the University of Colorado. But the simulations, we have them for a number of courses. Not all courses. Some courses lend themselves more to simulation. So they're also on the LearnChemE site. And the idea is, let's just, so each of these is a simulation. You'll notice that in addition to ours, there are a few that have been prepared by others that we've taken off the Wolfram site. So the Wolfram Demonstration project is where all these screencasts are located, in addition to being on our website. And it covers, you can see for thermodynamics, it covers a large number of topics. And if I look, rather than showing you, I'll show you this. It's a little easier if I show you on my computer than on the website. So these, for example, one of the reasons that we've made them in one of the types of simulation are things to explain diagrams better. And so this psychometric chart for, say, a material and energy balances course is something that makes it a little easier for students to understand diagrams, because unlike textbooks, you can simplify so they can see relative humidity lines, they can add in enthalpy lines, they can add in temperatures for some point, they can move that point around. And the idea is much better for understanding diagrams. So this is one type of thing that I think much better than, say, in a textbook for understanding charts, because that's certainly where I've gotten lots of questions always from students about charts, because they present one figure and they try and explain it with text. Phase diagrams in particular are particularly particularly useful, I think. This happens to be where you have two liquid, two components, and they phase separate. And the diagram is you can change the location of this point, and it shows how much of each phase. You can add heat. Now 3 phases, and you can add heat, and it'll stay at constant temperature at this temperature for a while until one of those phases disappears. And so it's a much better way of explaining diagrams. There are also some of these simulations have animation, in the sense that if I reset this is just looking at reversible and irreversible adiabatic compression. You can pick the final pressure, and then it tries to simulate reversible by showing continually adding the weight, and then it shows the difference in the final conditions. And students can, pick the final temperature. They can do expansion instead of compression. And then a few of the simulations are browser-based. Most of the 3 I showed you are made in Mathematica. You don't need a Mathematica license to use them, but you do have to download a free player. It's pretty short to install it on the computer. But this is we've made a few browser-based, and the idea here is that it allows you to, in this case, we're dropping metal blocks in ice water, and when we can change how many blocks and whether there's additional heat transfer with a stir, and then we can watch what happens. So you can imagine asking students before doing this to predict behavior, for example. That's how I would use these in an online class. Before showing the behavior, ask them which temperature is going to be higher, etc. And so I think some of these simulations would actually lend themselves quite well as a lab experiment. They weren't designed per se as that, but I can imagine, for example, saying, hey, since you can't get in the lab, use a simulation, change this variable, record how the system responds. For example, plot something versus something else. Now do it for a different condition. Actually write a report explaining the behavior. And so I picked an example, like multi-stage batch distillation, where you can imagine, let's look at the distillate composition as a function of how much evaporates. Let's look at how the temperature changes with the amount evaporates. Now let's change how many equilibrium stages. So you could imagine for this one in particular, making what would be the kinds of things you might do in a lab experiment, but it takes much less time, much safer, and yet it's reinforcing. So the idea is that you can pick equilibrium stages, you can pick reflux ratio, and then you can collect a sample. So it's pretty simplified animation, but you can see what temperatures are at different locations. You can then collect the second sample and watch, how the composition is changing. And there's actually quite a bit of data, if you like, that could be collected by using this simulation as a replacement for a lab experiment. Obviously, it doesn't accomplish all the things of a lab experiment, but it certainly can be reasonably effective. Now, part of the reason for using these that students are engaged actively, and that's, I think, all the studies say that's really important. The other aspect is students can use them and change the variable, say, hey, what happens if I change this? And they get the immediate feedback. And so the studies say it really helps them construct their own understanding of processes. And moreover, unlike in labs where students are worrying about the mechanical aspects and they're certainly afraid to raise the temperature to really high value. You can do it in a simulation with no trouble. And interestingly, there are studies by Carl Weidman in particular in physics that said students did better on exams if they did a simulation instead of a laboratory exercise. And even though they spent less time in a simulation, they understood the concepts better. Well, again, for those you might be hesitant, the feedback from students in the semester has been overwhelmingly positive, that students really use them, not all of them obviously, but a lot of them use them the way you like them to. I can test every scenario, and so I think that they've turned out to be really particularly useful. A few of these simulations are more of what you might call tutorials, step-by-step tutorials. They're located within the various courses on LearnChemE, and then they're also separated out. And this is a copy of the page. So this page in LearnChemE shows the simulations that we've called quiz simulations. And what that means is they're tutorials. And for example, for constructing a TXY diagram, it actually gives introduction, students start, and it says, move this point to where, you know, it should be located both in terms of mole fraction, in terms of temperature, using the date on the right. And then, you know, I didn't obviously read to see where it should go. And it says submit answer. If they're within the region, it, you know, because it'll show them a score. But it gives an instant feedback, and then they go to the next step, which is locate the other one, and then they continue through and they construct a diagram. Like they can move these points. And so hopefully this gives you an idea of what we mean by a quiz simulation. It's really moving through step by step. They have possibility for hints. They can start from the beginning and go through it again. They'll get different numbers. The other thing that we spent a lot of time and I think can be particularly useful for students working on their own is these interactive self-study modules. We have about 52 of them now, a more limited range of courses so far, but they include all the things that we've done in terms of what's on the LearnChemE site. There's some concept tests. I'll talk briefly about what they are. They're example problems in terms of their screencast example problems. There are, it says interactive screencasts. And what that means is we've taken some of our screencasts and inserted questions, because this idea of self-testing is, studies would say it's the best way that students learn if they're continuously testing themselves as they're going along. So it pauses, asks them a question, they put in an answer in multiple choice, then it tells them the correct answer, gives them feedback. Our interactive simulations are in these modules. Some of them have the quiz, quiz yourself, these step-by-step tutorials, but not all of them. That's why it's sort of grayed out. And so there are a couple concept tests for them to answer, and then they're given answer feedback. And there's a summary of key points. So these interactive self-study modules are available. A lot of it, material and energy balances and thermal, and then a small number for separations and a few more for fluids and kinetics. So obviously, depending on what course, how useful these are, but these are on the website under Quiz Yourself. And maybe just to give you a better idea of what's involved, if I go to one, it tells what prerequisites you should have, tells what you should be able to do afterwards, and then as you step through, it asks you to try and answer these questions right at the beginning, when students probably can't answer them, but studies would say that's good for them to think about it first. And then there's typically one or two, most of them have two screencasts to introduce the topic, then the list of the equations that are important, and then simulations, just to try and give students a better idea of vapor-liquid equilibrium. And so couple simulations. And then one of these quiz simulations that I just talked about. And then example problem. Most of them have more than one example problem. And then these concept tests. These are conceptual, not calculation questions. And then a summary. Here are the key points. So that's what the interactive self-study modules, they're, I can say, not for all courses yet. But again, students have been very positive, used them in thermodynamics, and some students use them instead of using the textbook, and they clearly like using them. Well, concept tests are kind of things that typically I would use in a classroom, but can certainly be used in an online course. And essentially what they are conceptually difficult questions that force students to think about their understanding. And in class, of course, the students then talk to each other to try and understand better their reasoning. But we have concept. Well, that was weird. Well, let me go to the page. Oh, I know why for that. So the concept test, you have to have a login. And when I went to my other browser, that browser doesn't have the login built into it. So this shows the courses where we have concept test, and obviously different coverage for different courses. But if you're interested in access, it tells you on the LearnChemE site under instructor resources, it says here to contact us at this email, and we'll give you access if you're faculty. We've tried to restrict it to faculty. Now these concept tests are also, I won't show you more. The concept tests are also, many of them are on the concept warehouse at Oregon State that Milo Koretsky and others. Most of our concept tests were put on when we set up that website. And again, he can give you a login. And then for those you may not be familiar, Cache has quite a few resources. You can see there for 16 courses. And this is the link. And so if I just look at one of the courses, but let me go online. They have how other people teach a course. You know, for example, Buffalo, fairly extensive course notes, videos, etc. There's links to our screencast, and then there are links to other screencasts on some of the sites. Links to simulations. Fogler has created quite a few of these simulation problems. Links to these concept tests, and links to various software that's useful. Links to other pages, again, for kinetics. Scott Fogler's book, his website has extensive material. And so the idea is, particularly someone new teaching a course, we think this site can be really valuable, and we try to keep it up to date and continue add new materials, correct mistakes, etc. So that's pretty much what I planned to talk about. I wanted to put my email here so that if you have questions in the future, I'm quite happy to try and answer them or point you in the right direction, someone that might be able to. And otherwise, I think we open things up for questions.
Fantastic. Well, thanks so much, John, for that overview. We're going to go ahead and open up for questions. You can do that in one of two ways. You can either open up your chat window and put a message into the chat window, or you can unmute your microphone and ask John a question. We have a few minutes for doing that, so we're welcome to start. I have a a few here already, John. So for young faculty who are now tasked with maybe going online, what does more online flipped classroom, this type of thing that you talked about, how does that typically affect things like teacher ratings?
Going to online, to the course completely online, you mean?
Yeah, so for young faculty who are
Yeah.
still worried about things like tenure, how does what is the typical student response to going online?
What I can give you is feedback on, like, we're using Zoom here for this presentation, and I've used to a limited extent, but some faculty have used pretty extensively to hold, for example, office hours using Zoom instead of being live, with students in an office or classroom, and students love it. They overwhelming feedback on those online office hours is super positive. Lots of students sign up. They ask lots of questions. The faculty member who's done that pretty extensively is like, well, yeah, it's one of the best things in the course. In terms of, like using Screencast instead of lecturing in class, again, the response from students has been really positive. The one thing, and this is something that Rich Felder has talked about quite a bit, anytime you make a change, you need to explain to students why, and typically more than once. So when I the first week of a class that I teach, I spend 10 minutes probably each of those first 3 days explaining why I'm teaching the way I'm teaching, because since I don't lecture and we spend the entire class on either students doing partially solved problems, completing them in groups, or doing concept tests and peer instruction discussions, I spend time explaining, here's why I'm doing it, here's what the studies say. And there are lots of studies that say online education is at least as good, if not better, than live. And so I think in terms of student rating faculty, the important thing is that you really explain to students why you're doing something.
That's a great suggestion. Okay, a question that came in said this was very useful. Much of the material is excellent for asynchronous learning. Any advice on how to blend this with synchronous learning with Zoom?
Well, I think I'm not teaching this semester, if I was teaching, I would end up using these concept tests and online, with the students all logged in, let's say it was regularly scheduled time, and ask them to think about it on their own, and then ask them for, what their answers are. In class, I use clickers for that, but certainly could, with the same chat option, have students input their answers, get an idea, and then ask, discuss what's the right answer, why it's the right answer. Lots of people pick the different answer, why that's the wrong answer. I think, involving students when you can't see them, it's even, I think, more important that you're not just lecturing for 50 minutes on the computer and they're, supposedly listening.
Great. Okay, so another question from Hussein. This is more about like learning management, probably software and platforms. But do you have any insight or input about online soft evaluations and homeworks? Not just quick quizzes, but moving to like software-based homework from paper-based ones, even for a person in class.
Some of our faculty use these, Wiley, their online system for homework problems. Sapling, our faculty use some of those for, the idea is each student gets different numbers. They may be doing the same problem, but they all have different starting values. seems like to me, a good idea in terms of efficiency, and that students getting immediate feedback, much less grading work by instructors. So, the problems when I talk to someone who's used them a lot is some of them aren't error-free yet, and that sometimes creates some problems. But I think that it makes sense. I'm not sure if I answered the question.
We'll let Hossein ask a follow-up question if there's still more he wanted to know. Another question. There's a lot of material there, but a lot of professors use, for example, Felder's textbook or other textbooks. Do you have any way those have been organized by textbook chapter topics?
Yeah. So let's look at for mass and energy balances. So I don't think we've updated to the most recent, but it's set up so within a subsection it shows the screencasts that are appropriate for each. So this is, I think, exactly what you're asking. And indeed, we do it for typically 1 or 2 textbooks, and we haven't actually updated to the Felder, Rousseau, and Bullard textbook. And we're always, it's a trick of finding enough money to keep having people to do that. But yeah, the simulations are not organized that way. But the concept tests are not organized by textbook, but under the instructor resources, there's something called course packages. And so material and energy balances, what this is, okay, you have to download so that doesn't, it's a complete OneNote file of how to teach the course, including which concept test to use for which section, which chapter, that kind of thing, and homework problems, exam problems, etc. So for thermodynamics, there may be 6 or 8 or 10 years worth of homework and exam problems, in addition to organizing the class by the textbook, which in this case is Elliott and Lear.
Fantastic. So another question, suppose somebody has content they would like to add to your list or provide screencasts as well. What's the way that an instructor can get involved?
Just email me. We certainly have, we've had some of the, for example, material and energy balances. A number of the screencasts were made by faculty at Lafayette College because we had a joint NSF grant that they were part of. We just added this controls page. That's why it looks a little different. But you notice they're from Johns Hopkins. Jeff Gray at Hopkins had contacted me and said, hey, you don't have any control concept tests. Would you like some? Because he had been using our material and energy balances once. And so we've been adding, and I think there's still more to be added, but we've been adding his control concept tests to the website. But so we certainly look at stuff. Sometimes people have showed us videos and they're like, well, no, it's a PowerPoint presentation. We don't think that's a good way to go, or it's 20 minutes long, and we've tried to set a upper limit of 10 minutes. Some of our very early screencasts a little longer, but yeah, certainly willing to look at and be great to get materials that could be added. Yeah.
Great. Another question. This is great material. There's also issues with sharing copyrighted content. What is the license for this content? And does the university need to obtain a license?
No, it's free. It's all, like all the screencasts are on YouTube. All of the interactive simulations are on the Wolfram project site in addition to our website, and the Wolfram is a Creative Commons, free for anyone to use. Now, a lot of this was made with NSF funding, and part of the idea is to make it available to people, so it's completely free.
Okay, great. Are there any recommendations on attribution if they wanted to cite the work?
I mean, yeah, we're happy if you let people know about the website by, putting LearnChemE.com somewhere, but that's up to you. I mean, we're certainly interested. The more people that use it, the better arguments we can make to try and get continued funding, to continue to add to it and correct mistakes, that kind of thing.
Okay, well, John, you've done a fantastic job at sharing some of the resources that you've developed over many years. Thank you so much for doing that. It's very timely, with many instructors who, may be doing this kind of for the first time to prepare content or kind of forced into online classrooms. I just also wanted to make everybody aware of another presentation that we're going to have next week, process control distance education. And we have a few speakers that are going to be for that. Jeff is on the line with us right now, Jeff Cantor at Notre Dame. We have Brian Douglas, who has the Control Systems Lectures YouTube channel, Anthony Rosetier, and then Steve Brunton at University of Washington, representing several different disciplines of process control. But let's, I just want to express my gratitude for John Falconer for presenting some of this material, the overview of some of the chemical engineering resources that you've developed over many years. So thank you so much for doing that. I hope you have a great trip down to South America.
Okay, thanks a lot.
All right. Okay, thanks everybody for joining.